Hello everyone! As a cheerleader, I frequently encounter a deeply frustrating issue. Before a performance, our team spent hours in the backstage dressing room carefully selecting a lipstick to create the perfect makeup look. However, the moment we step onto the stage under the intense, high-power spotlights, the lipstick color completely shifts, often look drastically different from what we saw backstage. This stark color assassin triggered my curiosity. To solve this real-world problem, my goal is to build a web-based system capable of simulating and comparing how different lipsticks render under various ambient light sources. Today, I will walk you through how I utilize a spectral radiometer to gather raw physical data and construct the color simulation system step by step. The first phase is physical measurement. We turned off all indoor lighting, isolating natural ambient light as our single experimental light source. On the CS2000, I set the measuring of angle or field of view to 1 degree, because lipstick samples have micro irregularities on their applied surface. Selecting the maximum 1 degree angle allows the lens to capture a larger sampling area. This averages out of the optical signals and effectively minimizes errors caused by uneven texture. Next, just like operating a manual camera, I rotated the objective lens focusing ring to bring the target area into sharp focus. Before measuring the lipsticks, we need to capture the baseline of our ambient environment, the spectral power distribution of our light source, denoted as S lambda. To do this, I measure an X-right color checker passport white balance target model. This target maintains an exceptionally flat and uniform spectral reflectance across the entire visible spectrum, with an industry-standard absolute reflectance of approximately 85%. Because it introduces zero color bias, it serves as our perfect baseline for light source recovery. I then use the instrument's software dongle to read and export this environmental data. Using the exact same focusing and measurement methodology, we sequentially scanned 6 different lipstick samples, capturing the reflected light spectrum of each lipstick under the current ambient light. We denoted this raw signal as L lambda. Now let's look at the underlying optical physics. To begin with, what is a color? Contrary to what one might think, objects do not have an intrinsic color. Colors are feelings, subjective perceptions created by our brain when our eyes receive light. The light from the sun, for instance, is a wave, which can be interpreted as the sum of several waves with different lengths. Like the different notes that make up a music chord, objects absorb some of these waves and reflect others. This apple, for example, contains pigments in its skin, which absorb short waves and reflect long waves. Our eyes are sensitive to these different wavelengths, and they transmit a signal to the brain, which gets interpreted as the sensation of color, red in this case. A lipstick is a non-emissive object. The color it displays depends entirely on the ambient light source and its own physical and chemical properties. This is governed by the principle of subjective color mixing. For example, if a purple light containing both red and blue wavelengths hit a red lipstick, the chemical structure of the lipstick absorbs the blue wavelengths and reflects the red ones, leading our eyes to perceive red. Mathematically, the reflected radiance L lambda entering the lens is the product of the illuminance spectrum S lambda and the object spectral reflectance R lambda. Our system can now project how these lipsticks will behave under any lighting environment. I extracted the spectral data of 6 representative standard illuminants from the official CIE website to model different real-world scenarios. The first one is D65, the standard daylight. The second one is D75, the north sky daylight. The third one is ID50, the indoor daylight. The fourth one is Illuminate 8 tungsten. And the fifth one is fluorescent F2. And the sixth one is typical LED. By assigning each of these light sources as our new S lambda and multiplying them by our lipstick's isolated reflectance R lambda, we calculated a brand new reflected spectrum L lambda for all 6 lipstick samples across all 6 illuminants. However, a calculated spectrum is still a continuous wave curve across wavelengths, which neither the computer screen nor human consciousness can directly process as a color value. Next, we must translate this physical curve to human visual perception. To differentiate colors, our eye uses 3 receptors, or cones, scattered across the retina. They each react to one of 3 ranges of wavelengths, corresponding very roughly to the red, green, and blue components of light. Our brain constructs the color we perceive from these three signals, as this is why space of colors systematically have three dimensions: red, green, blue, or hue, saturation, brightness. In color science, these biological sensitives are mapped by the standard color matching functions. Capital X equals k times the integral from 380 to 780 of S of lambda, R of lambda, X bar of lambda, d lambda. Accordingly, Y capital equals k times the integral from 380 to 780 of S lambda, R of lambda, Y bar of lambda, d lambda. Capital V equals k times the integral of 380 to 780 of S lambda, R of lambda, V bar of lambda, d lambda. Among them, Y value represents the absolute luminance, X value and Z value purely dictate chromaticity. Now that we have the human-centric XYZ values, we must map them to the standard sRGB color space utilized by modern digital displays. First, I implemented standard linear metric multiplication in the code. However, before rendering these pixels to a web page, we must apply a critical nonlinear processing step, gamma 2.2 correction. Human visual perception of brightnesses is nonlinear and operates logarithmically. Our eyes are vastly more sensitive to subtle luminance changes in dark shadows than in bright highlights. The sRGB standard resolves this by compressing the color data using a power law exponent of roughly 0.45 during encoding, which the display hardware then releases with a 2.2 exponent. By conquering these optical and physiological hurdles, our system successfully output the accurate color swatches for all 6 lipstick samples across 6 entirely distinct light sources, alongside an accompanying LAB chromaticity drift plot. The results scientifically confirm that shifting from a fluorescent lit backstage to a high-intensity tungsten stage creates an immense visual color discrepancy. This system now provides a rigorous digitalized foundation for costume designers and performers to predict the makeup appearance and conquer the color assassin of stage lighting. Thank you.